In this video, we're going to talk about the mean value theorem, which is the theorem that we will need in the proof of the first part of the fundamental theorem of calculus. So this theorem tells us that if we have a continuous function f on a closed interval from a to b, then somewhere in the interval, the function attains its average value. So notice that here we have a formula for the average value of our function, and for some x value equal to c within our closed interval, the function value there will be equal to the average value of the function. And this only holds as long as the function is continuous. So I'm going to talk about the proof and then explain a little bit about why this should be the case with just a real application. So to set up our proof, I've drawn a continuous function f of x, and continuous functions by this extreme value theorem will attain a max and min value in the interval that we're looking at. So let's suppose that we're looking at this from a to b, and the minimum value of the function is at lowercase m, and the maximum value occurs at capital M. And so we know by the properties of the definite integral that the minimum value of the function f, which here we're calling lowercase m, times b minus a. So this expression gives us the area of the rectangle that I'm currently shading that has a height, the height which is the minimum value of the function, and the width is b minus a. And we know that the integral of our function has to be between the two rectangles, the areas of the two rectangles. So we know that the integral from a to b of our continuous function f of x dx must be larger than the area of the rectangle that we shaded, formed with the height as the minimum value of the function and the width b minus a, but it then has to be smaller than the area of the larger rectangle that I'm shading right now, whose height is the maximum value of the function f, which we're also calling capital M in the graph, times the width of the interval, which is b minus a. So in this inequality, we can actually divide the entire inequality by b minus a. I'm going to assume that b is greater than or equal to a, which means that I'm dividing by a positive number. So the signs of the inequality will remain as they are. And then we have that the minimum value of f must be less than or equal to 1 over b minus a times the integral from a to b of f of x dx, which must be less than or equal to the maximum value of our function f. And so note that the expression in the middle, this is how we calculate the average value of a continuous function. And since f is continuous, and we're saying, well, this average value, this number, is between the minimum value of the function and the maximum value of the function. And because the function is continuous, this means that there's got to be some place between a and b where the function attains its average value by the intermediate value theorem. So the intermediate value theorem tells us that if the function is continuous on a closed interval, the function attains all the values within that closed interval. So the intermediate value theorem will tell us then that since this average value is between the minimum value of the function and the maximum value of the function, and the function is continuous, then there must be some value c in our interval from a to b, such that our function, in fact, evaluated at that value equals the average value of the function. And that is the proof of the mean value theorem, that if we have a continuous function on a closed interval, that function must attain its average value. If we think about what we get from this, just another way of thinking about this, right? in this bottom diagram, I've sketched a continuous function y equals f of x. And I've also written in green letters the average value of the function. And since this function is continuous on the closed interval from a to b, there must be some value c, some place c in ab, where the function attains its average value. What this also means, if I take this expression and I multiply both sides by b minus a, we get the following. We get b minus a, which is the length of the interval on the x-axis, times f of c, equals the value of the integral from a to b of f of x dx. In my diagram, the function I have is above the x-axis, so this is the area between f of x and the x-axis. On the interval from a to b. And this expression, well, this is the area of a rectangle because f of c is a y value at c, so it's that length, and b minus a is the length of our interval on the x-axis. So what this is telling us is that by the mean value theorem, there must be a place of value of xc between a and b where the area of the rectangle formed by using the height at c and the width of b minus a equals to the integral of the function, the area under the curve. And when that happens, that's our average value of the function. The average value is the y value at that place c, where this area in yellow of the rectangle is the same as the area in red, or the integral of our continuous function. So this is the mean value theorem, and I'm going to explain it just in words. Imagine that we take a day in June, for example, and we have all of the possible temperatures of the day, which is, an infinite number of temperatures that happen that day. And maybe the average temperature on, I don't know what I said, June 5th, is 75 degrees. Then because temperature is a continuous function, there must be some time during the day when the temperature was exactly 75 degrees. In other words, we could not have skipped over that average if that's the average of the function. That's because the function is continuous. If the function is not continuous, then all bets are off. For example, if you take 10 quizzes and you average your quiz grades and you get a 95, it's not necessarily the case that you got a 95 on one of the quizzes, because the quizzes are discrete values, so it is not a continuous function. You're not taking a quiz at every instant in time. So that is the difference between having a continuous function and attaining the average value versus having a discrete function where the average value may or may not be attained. Okay, in the next several videos, we're going to explore the fundamental theorem of calculus.